So as we often do, we'll start off with a definition here, right? The definition of a function starts off with two sets, right? And I think that the bottom right-hand example, I've got several examples we'll talk about here. The bottom right-hand example illustrates that idea the best. On the one side we have a set of people's names, and on the other side we have a set of animal names. Right, and what a function does is it's a rule or a pattern. But for us, a lot of times it's going to be a formula that assigns every element of that first set to exactly one element of the second set. I really want you to focus on that exactly one element part. All right, that's a key part of the definition here. And we're going to talk about that more when we look at these specific examples here. Some of these examples are functions. Some of them are not, right? Because they're going to, as you'll see, they don't meet that requirement. Now, these two sets have names. The from set, if you will, is called the domain, and the to set is called the range. All right, so let's look at these examples here and talk about which ones are functions and which ones are not. All right, so this first one here, it's Dow Jones sales volumes, I think is where I took this from. And right now, the only question I want to ask about these examples is, are they functions or not? Okay, you can see this meets our requirement that it's taking times, these would be the domain values, and it's matching each time up with a sales volume. And each time does get assigned exactly one volume number. Pick any time, pick a random spot on the x-axis here, and you go up, and it is paired with one and only one y value. So yes, this one is a domain. Excuse me, this one is a function. Okay, so how about this one to the right? X squared plus y squared equals 9. Okay. It establishes a pattern. It's a rule that assigns an x value a y value. Okay, yes. But is it a function? Well, it's a little hard to tell just by looking at it. If you know what the graph of that is, if you know that this is the equation of a circle, you might be able to jump right to the answer. But let's play with this a little bit. Let's see if we can approach this algebraically. What I want to know is how many y values does a single x value get assigned to? If it's 1, we're good. If it's more than 1, we're not. So let's take this and let's solve it for y and see what happens. So if I do that, we're going to move the x squared over, and we get this. And then we're going to take the square root of both sides. Now, there's one more thing I got to add here, right? When we're solving an equation and you take the square root of both sides, we're looking for all the y values here, right? The positive ones and the negative ones, and that's where the trouble starts. If you pick an x value, say let x equal 0, right? If we let x equal 0, then what do we get for y? Y equals plus or minus the square root of 9 minus 0 squared. That's the square root of 9, right? Square root of 9 is 3. And there you can see we have a problem, right? That one x value is being assigned to more than one y value, and that's not allowed, right? So this one is not a function. All right, so how about the bottom one here, bottom left, quarterly sales figures, right? Is this thing a function? Well, the quarter values, these would be the domain, and they're being assigned to a sales figure. That would be the range. And yes, every quarter is being assigned to one and only one sales amount. Right? So this is a function. Right? This one gets a check. So over here, Bottom right, I'm assigning people's names to pets' names, right? And the way we're doing this here is with the arrows, right? The arrows match values in the domain to values in the range. So is this a function? Well, no. Linda here is messing things up. She gets assigned to two different y values, two different values from the range. And for a function, that's not allowed. So that one is not a function. Okay, so we've got a bunch of examples here, right, to illustrate what's going on. Not only is this illustrating what is a function, what isn't, but you can also see the variety of ways that a function can be defined. You can define a function using methods other than a mathematical formula. You can do it with tables, you can do it with graphs, you can do it with diagrams, all sorts of options. All right, so there's a technical point that I need to talk about for just a minute here. Purists watching this, there are a lot of purists in mathematics, are going to be jumping up and down complaining that my definition of a function is incomplete. And technically, they're right. The definition of a function really needs to have two things. First, it has to have that pattern, whether it's a formula, or a table, a graph, whatever, and you also have to specify what the domain of the function is. Right? Technically, that is how you define a function. Now, for purposes of high school and undergraduate algebra classes, it's never done that way. Right? In fact, it's really exactly the opposite. And you'll see that on the next slide. Usually, you'll be given some kind of pattern, usually a formula, sometimes a graph, and you'll be asked to find the domain of that function. Right? And when we do that, technically what we mean is find the largest set, usually a set of real numbers, for which the formula you're given is defined. All right, so I'm going to continue with my definition of a function because it's the one that's used at the level that this lecture is intended for. But for those of you who may go on to higher things, just keep in mind that there is a slightly more formal definition where you have to come up with two parts, the pattern and the domain, not just the pattern. Okay. We're going to look at it. We're going to do a few more examples on this notation and making sure you're reading it correctly. Then we're going to talk about how to graph one of these piecewise defined functions.